Good morning and welcome to the second day of this big, great meeting we have here in Finland. My topic is Pyxidis, my favorite star for a couple of years now. We've been observing it with remote telescope in Chile. And it's a prototype of recurrent nova. And I was talking about recurrent nova law, even though we heard yesterday from Seppo and Ari about these stars and nova. But if you don't know, you can relearn. Okay, my main collaborator here is Brad Sefer from Louisiana State University. And on the same day, the world-leading expert of recurrent nova and nova at all. This is from December 2011. After I knew that Brad in Stockholm, he was there to receive the Nobel Prize of the Accelerating Universe project. He was working on the project. He didn't get the Nobel himself, but he was invited to the ceremony because he was in the same working group. His name is on the same paper. They got the Nobel Prize. The main writers. Okay, some example. We spent time in Stockholm with one day with Brad. We had a breakfast in his hotel and he drew a lot of exciting astrophysics on the napkin in the morning. So there was literally kind of recurrent nova events there and OC light curves and all kind of fine physics. Okay, then nova, what is it? It's a new star. Tycho Brahe discovered first one in 1572 and was published in the Nova Stella paper in the Cassiopeia over there, brighter than any of the stars in Cassiopeia. And now there's supernova remnant. It wasn't actually nova, but it was a supernova in the galaxy. Okay, it's all about stellar evolution. It's quite simple if you have only a single star. The more massive star you have, the shorter life it has. And the very massive stars, they form black holes and neutron stars and have a supernova kind of death. And light stars, they go like the sun, they go to red giant and planetary nebula and white dwarf at the end. And even lighter stars are much lower. So okay, the mass and time are related. So then if you have a double star, it has to be that one of them is heavier than the other one. So the heavier will evolve quicker. And if they are close together, the more heavy one goes to giant phase, and then there can be some matter flow to another star, and they will go into same envelope. So it's kind of one star with two cores in it, and it then will eject the outer cell envelope, and then you have a very compact binary star with a normal dwarf, red dwarf kind of star and white dwarf. And then time goes and the lighter component, the secondary star, will evolve to red giant. And now they are so tight, close to each other, then there will be normal cataclysmic variable. So there's a matter flow from the secondary star to white dwarf, and if it will and the secondary star will be ejected from the system. So this is the more or less current theory, what happens and what makes type 1a supernova.
But isn't there also a theory that at least some type 1a supernova would be caused by colliding white dwarfs?
Yes. This is the old theory.
Yeah.
Like
it is still on the leading theory.
Yes, it is. Yeah. Okay, and nova outburst. We heard from Arni yesterday what happens, but some recap. So we have a white dwarf and the donor star, matter stream going to the accretion disk, and then eventually to the white dwarf. Helium and hydrogen from the normal star, and it will form like a hydrogen ocean on top of the white dwarf. And when there is enough new hydrogen on this surface of the white dwarf, it will ignite. It will start fusion, and with the fusion, it heats very rapidly and causes the runaway reaction of the fusion. So basically all the hydrogen that has been accreted on the white dwarf will explode as a big fusion bomb. So yeah, then the cycle starts over. So it will accrete new matter over and over. And depending how long the creation of this hydrogen ocean and reaching the critical temperature and pressure, it will define how often those nova events will happen. This is a type 1a supernova. It happens when the white dwarf exceeds the critical 1.4 solar mass limit. And that's why they are standard candles, because we assume that they all are 1.4 solar masses. Same kind of stars, same mass, same luminosity, so we can measure the distance from the magnitude. Okay, recurrent novae, there are those novae that repeats less than 100 years. It's artificial human invention, this 100 years. It just it could be some other number, but we have defined that if it repeats less than 100 years, it will go. It is a recurring nova. But basically, it's just a nova. It just happens more often than the other nova. And to have less than 100 years between nova events, you have to have two things. The white dwarf mass has to be bigger than 1.2 solar masses to reach the temperature and pressure quick enough. And there has to be very high mass transfer to be able to get enough mass in time. And at the moment we know 10 of these recurrent novae on the sky, and half of them are found just recently. Probably we will find more when we follow up these novae longer. So we have very short observing history of novae, the faint novae at least.
Well, I think, if I remember correctly, this T Coronae Borealis is the brightest one.
Yeah, yes, yeah, magnitude 2 or so.
Yeah.
Yeah,
I remember.
It probably will be the next one that will. I have it in this slide, last slide. Okay, but the remaining big questions that has been assumed before is the mass accreted gaining some mass between nova outbursts. It has to be to become type 1A supernova. Okay, how will know if the mass is increasing or not? We can observe period change. If we can measure very accurately what's the orbital period of this double star, then we know if the mass changes. So we need to have an accurate period measurement, usually eclipse timing. If it's an eclipsing system, we can see the orbital period very exactly from the eclipse timing, but we have to make those observations before the nova event and after the nova event. For classical normal nova, it is very difficult because you don't know which one will explode. So you must have a recurrent nova, so you can observe it during the nova events. Because there are so small number of recurrent nova, and the nova events happens between tens of years. This is quite a challenging task. And the change of the orbital period is very small, much less than 1 second. Okay, these are the 4 better known recurrent nova. Pars Opticus, the Coriolis, the Pyxidis, and Muscorpi. And I've been observing these last 2. First, Muscorpi, so it was had a nova event in 2010. I used the same telescope in Chile to observe that. And then next year, the Pyxidis went to nova, and I started to observe it from the right after the nova event. This the magnitude range is like Veikko said, the Coriolis is 3.5 in the peak magnitude.
Prediction for T. Coriolis? Because this seems to be the next one, no?
Yeah, 8 years between last term, so
80.
Anytime, no. Yeah,
I think this
1866 and 19.
Also, you can't really use 2 data points there.
No, there might be a long big variation between those. But if you but for the Pyxidis, it was quite steady in the beginning of 20 years. 1902, 10, 20, 44, 67, and then we made it on the next eruption on around 88. It never happened, and now it was 2011. But it was quite stable before.
So I think T. Borealis could be a good amateur target also here in northern latitudes.
Yeah, sure, it will be. It's good work. The only it's very quick nova. It fades in 6 days for 3 magnitudes, so it's not observable.
Constant monitoring.
Long time. It might happen during one cloudy week or so. Yeah, so you better follow it. Okay, Pyxidis is my topic. I can finally come here. Oh, it's in Pyxis, Mariner's Compass constellation. The declination -32 degrees, so not observable from Greenland. And previous outburst, like I just said, was expected. 86, and it was a good example because Brad Schaefer, he got quite famous because he predicted the next outburst of Muscorpi very accurately. It happened when he said it. But this one, he wasn't so lucky because in 2009 he predicted that the next outburst will happen in 2052. And then he got second thought in next year on another paper, he thought that it kind of went to hibernation state, and it will take thousands of million or even million years before it will outburst next time. So he believed that it will become a kind of classical nova again. So, but as we know, it exploded in 2011, just after his second prediction. It's okay, I've been using this telescope to observe it. It's owned by Casey Harlington, a Canadian amateur astronomer who has set up different telescopes around the world. And one of his telescopes is here in San Pedro de Atacama in Chile. And I helped him to set up this telescope in 2007. And since that I have been granted some observing time. Basically, at the moment I'm the only observer, only user of this telescope. It's a plane wave Dalkirkham telescope, 0.5 meter aperture on Paramount ME mount, and that's very good Apogee Alta U42 CCD, back illuminated chip and everything, high-end CCD. And this is all sky picture from 2011 something, December, around Christmas 2011, because there was this comet Lampsoi on the sky, and it was nicely visible on the all sky image here. And Pyxidis is over there. There is Sirius and Canopus over there, and they form quite an equilateral triangle on the sky. It's on the other side of the Milky Way over there.
I think that might just be observed from where I live, because I can see below Sirius. So possibly.
Can you see Canopus? This is south here, so it's minus 22. So you should be. But it's very low. Very low.
Southern Finland, I think it's about minus 25. That is still somewhat observable.
Yeah. Okay, and the EuroVS light curve from 2011, so April 2011, it was a nova outburst, and it was even observed during the rise. It was caught by amateur observer visually from Hawaii, and on the same day we were able to get some CCD observation. I think it's the only recurrent nova that has been caught with CCD while it was rising, the nova outburst. And it peaked about 6th magnitude here, and then was fading for us. There are different bands. Red is I band, and blue is blue band, and green is V band observations. It's different from what Arne saw yesterday. It's the normal nova that we stop observing around here, but this one is still followed. But most of these data over here are either mine or just examples, except this visual observers. And then here's my light curve. I've been observed more than 200 nights, and I've got more than 60,000 data points already in this stars. This star. It's all one night drops here. Again, the first paper we published on this star was 2012, because the light curve of this eruption was significantly different from the light curve of 1967 outburst. We expected it behave. This green one is the old data points. So it was first following quite nicely of the old light curve, and then over here it was summer 2011. Yeah. Okay. Then there we expected that the star will fade rapidly like it did in 67, but it didn't. It did get a bit brighter at the time when the quick fading was expected. And since then it was going quite smoothly. So big questions for theorists is why the light curve is so different. Because it should repeat exactly the same every time. Because the system is it's the same, like the mechanism is the same. In the same star, so it should behave similarly during its outburst.
But even in the beginning, it's different. Yeah? I mean, how can you imagine a similar behavior if I mean, this is a explosion and probably it's chaotic, that it follows exactly how it was seen last time.
Yeah. But they should be the same, because there should be then some physics behind it, what makes it different every time. So it's difficult to explain, difficult to model why it's behaving so differently.
They just out of this, it seems most reasonable to assume that the change had something to do with the accretion process.
Yeah, and that's why it was 40 years.
So you have the explosion and you still have something around it which affects those.
Yeah.
And that can be very different.
Okay, and then in October 2011, I started to see some periodic changes on the light curves. There's each of these is one night light curve. So this is all one night over here, one day, or less than one day. But the star was fading night to night, but I was kind of seeing some changes on the light curve, even if it was very small amplitude. But it looks like something is going on instead of steady fading. As I was already more or less bored of this star because every night it was just flat light curve and bit fainter than the previous night. But then I was getting interested. It's doing something. And I used Arto software to search the period. I first detrended all the fading night to night. And every night I subtracted the average magnitude and used the ANOVA method to search the period. And it showed one quite nice period on the power spectrum. And this is the whole data set of just something like 1 month of data folded to this period, and it was quite clear that it had this 1.8 hour period. It's very small amplitude this paper. So it was astronomical telegram we put out with Brad, and he insisted that I am the first author on this paper because it was my discovery. And basically we say here that we detected the highly significant period signal. That is it's the previously known orbital period of the star, and because it quite accurately it's plus minus all 2 seconds of the period.
So it was known before?
Yeah, it was known. It was observed before the nova outburst. It's the same, more or less the same period that was before. And then also the amplitude it's not very big. It's about 5 millimagnitudes only. But then in next month the signal got significantly bit bigger. But also the star is kind of flickering a lot, and the light curve is not the same every night. So it makes this periodical signal only when you take average of many nights. Okay, and then another paper published just last month by Joe Patterson from the CBA, and there's I'm the first co-author, Roberto from South Africa, and Josh is here as well as the fourth co-author. And we claim here that the period has changed a lot. This is from the same paper, more or less the only plot on the paper. It's a very short paper. It will be coming a bigger paper later. But this short paper showed already that Joe and CBA, we have tracked the star very long time, since 85, when it was expected to become a nova. We followed it to 20 years, and it showed a steady orbital period increase because of the accretion. So it's a slow system. But here, when the nova outburst happened, it jumped very high, very much slower than before. And there is some physics behind it. There is some you lose the mass, and you might lose some angular momentum, because depending which direction the matter flies away. But the angular momentum loss can only decrease the change. So we got to this conclusion that during the last 45 years, the mass accreted was much less than what was lost in the nova outburst. It lost 5 to 6 times more mass than it could have accreted during the 45 years. And this is a minimum limit. So you can change some unknown parameters, but they all make the ejected mass even bigger, not less. Okay, the observations are still going on. I'm still using Casey's telescope in Chile to observe this star. Not every night like I did before, but more or less once per week or all time for a month now, because we don't need to follow it so often. And then we got fast track observing time from Nordic Optical Telescope last year in April, about more or less exactly 1 year ago. We did spectropolarimetry, and we could see some magnetic fields and so on. And then we got observing time with BLT, and me and Seppo went there to observe in February this year. Okay, this is same spectra that Seppo showed quickly at the end of his talk yesterday. This is Pyxidis from Nordic Optical Telescope, and it just shows some emission lines. This is H alpha, and these were something like nitrogen over here, and it's helium over here. And polarimetry from these spectrums. This is the spectra of wavelength, and then the it's very puzzling because on the data set we have, it shows this same polarization on phases 0 and half. So kind of 2 poles on the white wall. But then we observed it 4 hours. So this should have repeated on the second orbit, but it didn't. So we have 2 very significant detections of polarization during the first orbit, and then nothing on the second orbit. So we don't know what's going on.
So there's a branch going.
Yeah, something like that. Yeah, something like that. Yeah. Okay. We have some ideas, but we don't know yet what happens.
That's very strange.
I gave a few slides of my trip to Chile. In February, we flew to Santiago and then to Antofagasta, and then took ESO bus from Antofagasta to Paraná. It's like a real desert over there, nothing growing. It's like a moon or Mars, except on the residency hotel on the Paraná. It's like a garden underground. You might have seen it on James Bond film, Quantum of Solace. Film was what was the bad guy's headquarters. It's a nice swimming pool and everything. So we were there three nights, and 2 days were for acclimating and preparing the observations, and the last night was the actual observing. Here we prepared the observing sets with Seppo and the support astronomer we were having. Very nice sky, of course. Unfortunately, it was quite bright moon, so we have had only 2 or 3 hours without the moon. But then it was like this when you stood outside. It was the residency hotel is over there, and just stepping out from the back door, you see something like that, Magellanic Clouds and center of the Milky Way. Breathtaking view. Okay. We observed with one of these 8-meter VLT telescope using the UT1 Arto telescope. And we had the whole night. We started at the sunset and stopped at the sunrise. This is a UT1 over there. This is UT3 over there. Sun is just setting. And we are inside the UT1 dome. It's very it doesn't look like an observatory. It looks more or less like a modern factory or something like that. And it works like a factory. It's everything is automated.
Science factory.
Science factory. Yes. And this is the Force 2 instrument we were using. Quite big spectrometer on the Cassegrain focus of UT1. At the control room, we were allowed to use only one terminal here, just to select our observing blocks. They had to be prepared before. There was no change during the night. We only selected, now we observe this observing block, and then it went to instrument computers here and telescope control computers here, and they had own operators that run the telescope or the observatory. We were just telling them what to do. There's a first spectrum on the display, right here. We did spectropolarimetry, so we got always 2 spectrums, one with other polarization angle and other with the other. So when we doing the spectropolarimetry, we kind of subtract these 2 spectrums from each other. Very complicated stuff. But here's one raw spectrum from VLT, from red, from blue. From blue, and it shows oxygen 3 emission lines, and it's there are kind of double lines, and the basic explanation for double lines is that we see accretion disk, and the other feed comes from the other side of accretion disk that is going away from us, and the other one is coming to us, so it's represented widely. But this is a big problematic because the current model of Pyxidis is that it's a face-on system, so we see it on the top. So we shouldn't see any double emission lines. I don't know, I think maybe the model is wrong.
The other lines, they are not double, so are they also from Pyxidis or just from somewhere else?
I don't know, this is just a hot pixel, and I think this is doubled, but you can't see because it's so faint, and this is some atmospheric from atmosphere, some of those lights. This is raw spectra, just from the raw CCD image. It's not flat fielded and not done anything, just I took just the intensity plot of the spectrum. So I think this is double, but this is not, and this is a hot pixel. But you can even measure the speed of the rotation speed of the accretion disk from the difference. Okay, and then we did some deep sky imaging as well, because we had to point the telescope between two filters, and I asked if it's possible to take a longer than the 2-second pointing exposure we was supposed to do, and the operator said, yeah, we can expose longer, and we took a 30-second exposure with red filter, and you can see the nova cell around the Pyxidis. It's single 30-second exposure. It's a very, very faint nebula around there. It's probably from the 1890 nova outburst. And there's some, this is from VLT as well. Very long exposure, showing the nova cell much better. And here is a Hubble Space Telescope picture of the nova cell. We can even see some details on the structure of the cell.
This is also seen in the VLT.
Yeah, this is from the VLT.
Yeah, but the structure is also seen. I mean, a similar structure than the other one.
Only,
I mean, you can see moving.
Yeah.
The extension.
Yeah.
During party, I mean,
you can see it's expanding. Yeah. And we are trying to measure from our picture compared to these two, if we see some movement. Okay, some open questions. Did the period change? Yes, we detected the period change very clearly. And did the white dwarf gain mass? No, obviously no, it was losing mass. And so Patterson claims in our paper that it will die, it will eat out the whole system, because it's injecting more and more matter. And so it will not become a supernova to type 1a. And Brad and I, we are just publishing a paper in Nature that we are claiming that no recurrent nova will ever come as a type 1a supernova. So that road is blocked by our view. But then we don't know yet if the Pyxidis is magnetic. The answer should be in our data set from NOT and from VLT, from the spectropolarimetry we just did, and we are waiting to Seppo to make the final analysis. But it looks like now it is magnetic. But we still don't know what causes the optical signal, and it's the 1.8 hour signal. I think that we have something like this. The system is something like that. It's not face on, and it's probably intermediate polar, so it has a kind of green accretion disk. And this should make this couple emission lines, and probably the magnetic field, it must have a big magnetic field, and these circular polarizations that shows in our NOT dataset, it comes from these two jets going to the magnetic poles of the white hole. And I don't know why we don't see it all the time. Maybe these jets are sometimes off, no matter is flowing, and sometimes it is on, I don't know. Maybe something else is going on there. But it's, even if it's kind of a prototype system, we don't know much about it. We have some assumptions. This should be like this, but the data looks like it isn't. Okay, and for theorists, some big questions is why it happened now, why it didn't happen after 20 years as before, and why the light curves are different. Okay, and the probably next known recurrent nova will be the Corona Borealis. It's the star is over there. And the prediction is 2026, but as we know, it can be before or after. Nobody knows when, and it will peak about 2.5 magnitudes. Easy to see. About the same as this alpha star gamma. So keep an eye out of it when you see Corona Borealis on the sky. Just check if there is an extra star over there.
I think it's quite easy to monitor because it's about 10.5 magnitude.
Yeah.
Almost 10.
Mm. Yeah, it is to monitor. At least it's easy to see when it's as a nova.
And people are also nervous of the pre-eruption period of that system.
Mm. True. Yeah, true before. Yeah.
So also the period, rotation period of the system, is that observed?
Yes, it is, but it's very long, and it shows a spectroscopic period, but not photometric. And it's quite faint. It's quite faint star at the moment. So.
Of course, CW Corona Borealis is a close near contact binary in that same constellation.
Okay. That's all. Thank you. Questions? You ask questions during my talk.
I have actually a question concerning the scope. I mean, it's a 20-inch plane wave. The scope they were using there in something. I mean, are you happy with it?
Yeah, I'm quite happy, yes.
No problem with the mirror and
No?
the support of the mirror because it's glued?
No, it's the shape of the stars are not exactly round, but it doesn't matter for photometric.
Yeah, I know.
Yeah, it might use some tweaking for pretty pictures, but for photometry it's just...
You see that?
Yeah.
The shapes are not...
Yes. But I think they are more or less the same all the time, so it's some collimation problem. It's not properly collimated, so I see it in all directions. It doesn't change when you point different parts of the sky.
Because I have mentioned something about astigmatism because of the heavy mirror, the changes in temperature, and the support of the mirror. I mean, in the sense that it is
Could be, something like that. Yeah. But for photometry, it's a problem. Even when there is a good scene, I have to defocus just a bit to make the stars bigger than 255 pixels. So I don't care if it's not perfect the picture because I want to have it get better,
Yeah.
better photometry, yes.
I mean, what is the size of the pixel in the CCD? You know?
It's 0.0 arcseconds on the sky. What are the physical size?
Well, how many arcseconds in the sky?
0.8.
0.8.
Huh?
Mm-hmm.
So with 2 arcseconds seeing like 2 pixel stars. But usually it's around 3 arcseconds over there for all of your images.
I always use 3 times 3 billion, so I don't even look at the.
Okay, so then you have very small stars on the final image then.
Yeah, no, not so small, yeah, because I don't focus and I don't look.
Ah,
Image.
yeah, okay, you don't.
Yes, I mean I'm the same, but okay, I have a friend which is pretty picture minded, and we are thinking of buying a 20-inch brainwave.
Yeah.
But I know from Anna that this is a problem.
Yeah, I would say richer gradients are better for if you want to crisp, good quality images. I would take some richer gradient.
It has to be corrected as well. I mean, the field.
Yeah,
You have a large field.
Yes, you
You need a corrector. I mean, this is corrected.
Yeah.
This is a corrected system.
Yeah, but it's like having a corrector all the time on
Yeah.
the telescope. So
Yeah.
with richer gradient you can choose if you put the corrector or not.
Yeah, but not remote. I mean, you can tell Anna you should change today and you should change tomorrow.
Yeah, of course.